So a funny example is this is something that happens in high school, sometimes in engineering clubs or engineering classes in different contexts, but it's called the egg drop. And you have to build an apparatus to protect an egg in a drop. So what that might look like is, let's pretend that the apparatus you build is just a little cardboard box. And you'll see that this is a bad, flawed design. So here is the box, and there is the egg inside the box. There's the egg, and the box surrounds it. And you drop it from a certain height, and it picks up momentum because gravity is the net force. The weight force is the net force on the box. It's accumulating up momentum, but that's not what I want to talk about now. I'll have an example of that I calculate for you in a later video. You just know that it picks up momentum. So here is the egg and the cardboard box right before it hits the ground, before impact. And then after impact, here is the box, likely undamaged. But the egg, you know, the egg is just destroyed inside the box. So here is all the egg. So it's broken like that. And I'm just spitballing with values, but during impact, right, there is a delta t that took us from t1, this is the moment in time before the impact starts, and then this is immediately after everything has sort of finished. So we'll say this is t2. So t2 minus t1 is our delta t. And during the impact, though, the average value of the force on the egg is, especially by the bottom of the cardboard box, this average value may have been 20 newtons. That's definitely big enough to crack the eggshell, which is why the egg broke. Delta t, though, on the other hand, the egg broke in a really small amount of time. So let's say this is about 1/10 of a second. The impulse delivered by that 20 Newton force during that small amount of time is 20 newtons times 1/10 seconds. It's equal to 2 newtons seconds. So this is the impulse, and this, by the impulse momentum theorem, is the change in the momentum of the egg. So that delta p represents the fact that the egg had a bunch of downwards momentum right before the impact, and then changed into 0 momentum for after the impact. So that's what delta p is associated with there. On the other hand, a successful version of this is to, so here it's the same thing. I've got the, sorry. I want to change the shape of the apparatus, right, the engineered apparatus, to being something of a cone. So if I can cause, say, the egg to be carried in a cone like this, then by the time the cone crushes, so here is the egg, and that's the crushed part of the cone. What this does is it changes delta t. I'm going to be a little bit extreme. Delta t might go all the way up to a full second. You extend the time. And if you extend the time of the impact, you don't need as large of a force. It turns out that the force goes down to 2 newtons. That is, if I increase the amount of time by a factor of 10, then the average force required goes down by a factor of 10. And earlier, damage is not because of impulse, but because of large force. Here's the large force that broke the egg. Here's the small force that did not break the egg, but was able to cause the egg to slow down enough and lose all of its momentum. But nonetheless, J is 2 newtons times 1 second. It's the same value. Same impulse affected the same change in momentum, but in one case, the impulse involved a strong force that broke the egg. In the other case, the impulse involved a small force that did not break the egg. Okay, so I'm going to continue. So in this, I told you to think conceptually. You kind of back off all of this very serious, careful mathy stuff that's really hard to calculate and also really difficult to think with. You relax a little bit, take off the vector symbols, keep in mind directions and stuff. You have to still be careful, but you're now becoming more of a physicist with the topic. Here's a particular situation where we got to be a little bit of a physicist about the topic. If you're very careful, you would realize that actually the impulses that I had to calculate would in some sense be negative, because my momentum, the final value is 0, the initial value is p downwards, so 0 minus p is p upwards, right? So there are some directions in here that I didn't deal with very carefully, but nonetheless, you can see the argument unfold, right? We just wanted to think about the strength of the force involved for a given impulse. Common impulses, different forces. But if you want different forces, you have to change something about the time. This is the idea in the impulse idea. Okay,